Hello and welcome to a short lecture on a magnitude comparator. We've already taken a look at another lecture, an equality comparator, and the equality comparator is part of the magnitude comparator. All right, we'll take a look first at a one-bit magnitude comparator. We'll look at how to create it schematically with Verilog, how to create it symbolically, and we'll move on to a two-bit magnitude comparator and talk about how to derive its equation, structurally represent it with a schematic and Verilog. Right. So a magnitude comparator is a combinational circuit that compares binary numbers, right, in order to find out whether or not one binary number is equal to another, less than another, or greater than the other binary number. Right, so typically we could generically represent the circuit as having two inputs, A and B, where A and B represent these binary inputs. Right? The n-bit comparator, well, n-bit relates to how many different bits we have in our inputs A and B. Right? So for a one-bit comparator, then A has one bit, B has one bit. And you can see then that the circuit will generate three different outputs. Right? It'll generate a 1 when A is greater than B. It'll generate a 1 when A is equal to B, generate a 1 when A is less than B. And none of these three can occur at the same time, right? When A is greater than B, it's not equal to B, and it's not less than B. So let's take a look at the truth table. So we have our inputs are two single-bit numbers, A and B, and we have these three outputs, right? And so for 2 bits of input, right, we have 2 squared, 4 unique binary combinations, is seen here in the blue. And then over on the right, let's talk about how we derive then these outputs. Right? So LT stands for less than. It will be 1 when A is less than B. So we're comparing A and B. Right? And so in the case where A is 0 and B is 0, A is not less than B, our output is a 0. When A is 0 and B is 1, 0 is less than 1, so A is less than B, our output is a 1. When A is 1 and B is 0, 1 is greater than B, so it's not less than B, our output is 0. Right? And when they're equal, our output is a 0. So there's only one case in these 4 unique inputs, right, where A is less than B. To derive then greater than, well, we're going to say, is A greater than B? So when A is 0 and B is 0, is A greater than B? No. When A is 0, so when A is 0 and B is 1, well, 0 is not greater than 1, so our output is 0. When A is 1 and B is 0, yes, A1 is greater than 0, A is greater than B, so our output's a 1. When A is 1 and B is 1, it's not greater than B, our output's a 0. All right, so we have one case then where A is greater than B. And then we have 2 cases where A is equal to B. Right? When A is 0 and B is 0, it's equal. When A is 1 and B is 1, they are equal. In the other 2 cases, they are different, so they're not equal. Right. And so we can then derive equations for this circuit. Right? We have to derive an equation for every single output. We have 3 outputs. So our less than output is a function of A and B. Well, there's only one place here. I'm solving for the ones. Right? I'm solving for the min terms. Right? In the sum of products form. So when A, in this case, A is 0, B is 1. So our min term is A not B. Right? For greater than as a function of A and B, well, there's only one case. A is 1 and B is 0. The min term is A and it would be not. And then we have 2 cases where they're equal. And in that case, we have A naught, B naught, ORed with A, B. And we know from our study of exclusive NOR gates, that's the XNOR gate. The XNOR gate is known as the equality gate. So we could further minimize that by saying, let's XOR A with B and invert it. All right. So that's how we create a one-bit magnitude comparator, right? We, like any other circuit, we describe the behavior, we generate a truth table, and we generate equations, Boolean equations for the outputs. Right. And so if we were to draw this, right, for all 3 of these circuits, over here on the left, we have our inputs A and B. All right, we have our NOT gates here. This one provides A naught. This wire here provides B naught. And so let's take a look. Here's our less than. Well, less than is A naught ANDed with B. right? So here's B coming in here. We said the greater than is A and it would be not. That's this circuit, so that comes to our greater than output. And then we said, well, equality, that's A XNOR with B. We have this XNOR gate, and that goes to our equality output. So that's how we could schematically represent this circuit with logic gates. And so I went ahead and ran a simulation of that, right, to show that that drawing was correct. And so we have our two inputs, A and B. And so our output EQ is a 1 when A is 0 and B is 0. It's a 1 here, B is 1, A is 1. It's a 0 in the two cases where A and B are different. Let's take a look at greater than. Right, greater than is a 0 everywhere except for here. A is 1, B is 0, so 1 is greater than 0. In this case, A is greater than B. And then less than occurred once, and that was when, right, A is 0, B is 1, and so we have a 1 on the output of our less than circuit. So the functional simulation shows that the way it was generated from that schematic, so it shows that that schematic is correct. We can write this in Verilog as well, right? And so I called this module 1-bit mag comp. Here's our inputs, A and B. Actually, keyword wire should go in there. If you don't use the keyword wire, it assumes it's a wire. So input A and B, output less than, greater than, equal to. And we just write our three expressions here using a continuous assignment statement. We assigned LT, right? Not A, and it with B. GT, A, and it would not be. EQ, A, X, nor B. And so there's your Verilog implementation of that. Similarly, we talked about in our lecture with equality comparators, we started talking about structural representation and how we could make a symbol that represents a circuit. So we could make a symbol then that represents that circuit behavior. In this case, I made the symbol from the schematic. We can also make a symbol from the Verilog as well. Right, I generated this symbol in the Quarta software. You can see then that we have this, what we call this abstraction of the circuit. We know that the inputs A and B are over here on the left. Right, we have three outputs from this circuit, but we don't know the circuitry inside that created this if we were just working from the symbol. Right, sometimes when we work from a symbol in a library, we only know the behavior of the circuit. Right. Right. And so if you want to use that right in the schematic, you could just wire up two inputs. You don't have to name them A and B. I could have named these X and Y. We could compare to see if X is greater than Y, X is equal to Y, X is less than Y. Right, so we don't have to use the same names out here. On the outputs out here, I happen to call this output ALTB, that stands for A less than B. This is a GTB, A greater than B, and A equal B, right? Hooked up to those. All right. Let's move on to the 2-bit magnitude comparator. The 2-bit magnitude comparator, then each one of our inputs, A and B, are 2 bits wide. And so we have a total of 4 inputs. 2 to the 4th is 16, so we have 16 unique binary combinations in our truth table. Over here to help us out, I also added 2 columns to say what the decimal values of A and B are, right, when we want to go ahead and generate the outputs. So decimal value of A is 0 here, but if you look at here, the binary input 0, 0, so we have 4 binary inputs of 0, 0. In all of these cases, A is 0. When the binary input 0, 1, right, the decimal is 1. Same way here, when B is 0, 0, the decimal value of B is here, when is 0. When B is 0, 1, the decimal value of B is 1. All right, and so we then, again, these outputs tell us whether A is less than B, greater than B, or equal to B. All right, and so this less than truth table was generated by saying, okay, here's A, here's B. Is 0 less than 0? No. Right? A is 0, B is 1. Is 0 less than 1? Yes, it is. A is 0, B is 2. Is A less than B? Yes, it is. Output's a 1. A is 0, B is 3. Is A less than B? Yes, it is. So if you go through this truth table, then you can see, right, we have a 1 everywhere where A is less than B. Similarly, everywhere where A is greater than B, so in this first case here, A is 1, B is 0, A is definitely greater than B, we have a 1. So the ones were generated in these cases were A is greater than B, 3 is greater than 2, 3 is greater than 1, 3 is greater than 0, 2 is greater than 1. And then finally, right, for equality, everywhere where A and B are the same. So when A and B are both 0, when A and B are both 1, when A and B are both 2, and when A and B are both 3, they're equal to each other. So there's where your 1s come from, right? 0s everywhere else because they're not equal. Right. So very similar, right, to the 1-bit, we could go ahead and generate Boolean equations for these circuits. And so if we want to write things in terms of min terms, right, our less than is a function of A and B. Well, that's going to be the sum of min terms 1, 2, 3, 6, 7, 11. Right, you can go through the truth table, see if that's correct. Greater than, right, 4, 8, 9, 12, 13 equals 0, 5, 10, and 15. So those are all the cases where we have the ones. So after you have that expression, you could go on to solve that. In this lecture, we're going to solve greater than. There's another lecture out there that's already been presented that shows you how to solve the case for equality. So we won't go through that here, but we will solve the greater than. Right, so if right here in our next slide, I've taken then the greater than, right, expanded, put the ones in a K-map, right, and then shown the grouping. So here in yellow, we have 4 that we can group together. In green, so these 2 green squares mean that this one is grouped with this one, and then the blue around these 2 means that this grouping has taken place. So when you go ahead and reduce it, you end up with an expression, this particular expression down here, that solves for greater than, right? And here's the truth table over here. I'm only showing the greater than column, right, to make it a little easier to read. So you can then see, right, you can map these ones to your K-maps. So for practice, I would suggest that as you go through this lecture, right, you stop now, create a truth table, fill in the values, right, the 0s and 1s, create your own K-map, see if you get the same expression before going on. All right, now that we have that expression, I want to think about the 2-bit case, right? And just the cases where we have the 1s in the truth table. So what I've done is I've reduced the truth table here to just the cases where A is greater than B, right? I'm showing you the decimal values here, right? The decimal value of A is greater than the decimal value of B in all of these cases. And here is the input combination that generates that. And so we can take a look at this. We're going to see that, right, we only have then these 6 cases, right? And we're going to move on to what we're going to do is we're going to write the equation in a different way. So we have these 6 cases where A is greater than B. We'll come back and look at a version of this truth table after we derive these equations. So now I'm starting from the canonical, right? Starting from the canonical expression. So canonical means we list every single term. Right, and I'm solving in sum of products. I'm solving for the min terms. These are the ones of the truth table. So here's our canonical expression, not reduced. And then I'm going to use the commutative and associative laws, the commutative law to rearrange the ORI, the associative law to form this group. Right, so once I've grouped I'm grouping all of the terms with A1, B1 not together. There are 4 terms that have A1, B1 not together. If you remember back in our K-map, right, we had 4 terms that we grouped together. Those are these 4 terms. All right. So once I group those together, what I want to do is I want to use the distributive law to factor out the A1, B1 not. We factor that out, we have this expression. And I haven't done anything with the other 2 terms, they stay the same. And now that we have this expression in here, I want to go ahead and factor out the A0 not from these 2 terms and the A0 from these 2 terms. Right, use the distributive law to do that and rewrite the equation in this form. When we get to this form, we can see that we have B not, so B0 not ORed with B0. That will be a 1, right, by the inverse law. X ORed with X not gives us 1. And so both of these terms are going to reduce to 1. That's what this says down here, that B not ORed with B0 equals 1. And then when we end anything with 1, we get the same term back. No, this is just going to reduce to then, right? I have my A1 and with B1 not. This inner term here is just going to reduce to A naught, A0 not, or with A0, right? Keep the other two terms the same. And then we can recognize that this term will reduce to A is 1, is A0 not, or with A0 is going to reduce to 1. Anything ended with 1 gives us the same thing back. We apply those two ideas to get to this form here, where we just have that equation A1, B1 not. Same equation we got out of the truth table. Right. But what we did in the truth table is we then further reduced, right? We were able to group and further reduce into sum of products form. But here, what I want you to recognize now is let's factor out, so this term, A0, B0 not, A0, B0 not is in common, right, with both of these terms. So we're going to use the distributive law to factor that out. We end up with this inside, and if you look at that, that is the pattern of our XNOR gate. Right? So we'll simply then change that to the XNOR relationship, and we'll then say that a minimized form of our greater than comparator is this expression here. Right? A1 ended with B1 not, or with A0 ended with B0 not, ended with A1 XNOR with B1. Oh, that's a mouthful to say all that. All right. So like I said, you should practice your Boolean algebra. Take the ideas that I just talked about. Right, go ahead, and I would minimize this lecture. Go ahead and write your equation down and see if you can factor out, follow the Boolean algebra, and come up with the same expression. It's good practice. Remember, these things show up on exams. All right. So here is the minimized expression we just had. And let's take a look at behaviorally what's going on. So what does the term A1 and with B1 not mean if we were to put it into words? Well, what it really says is that A1 is greater than B1. And why does it say that? Well, we know in this particular term that A1 represents a 1 and B1 not in a min term represents a 0, right? Anytime we invert a min term, that means that the binary input was a 0. Well, 1 is greater than 0. So we can say that this expression means A1 is greater than B1. Let's take a look at this term here. That term says that A1 equals B1, which we showed before with our equality comparator circuit, right? And we know that the XNOR gate is the equality gate. Finally then, what does this term say? This term, A0 and with B0 not, says that A0 is greater than B0. Well, it's very similar to this term, right? We know that A0 represents a 1, B0 not represents a 0, so 1 is greater than 0. And so if we were trying to put the Boolean expression into words and put these three ideas together, right, this Boolean expression says if A1 is greater than B1, remember, if A1 is greater than B1, or, there's our OR gate, or if A1 equals B1, A1 equals B1, and that is ANDed with this, and A0 is greater than B0, then A is greater than B. Right? A can be greater than B when either one of these is true, so when this term is true or when this term is true. That's where this OR comes from. Right? The AND down here, right, comes from the fact that this relationship is ANDed with this relationship. Now that we've put this into words, we're going to be able to use a 1-bit magnitude comparator to build a 2-bit magnitude comparator. Because if you think about it, a 1-bit magnitude comparator has an output for two 1-bit inputs that can tell us when A is greater than B. So this can be the output of one magnitude comparator, the greater than. Here, where this says A0 is greater than B0, that can be the output of another magnitude comparator, the greater than output. And then this will be the output of, right, the equality comparator inside the magnitude comparator. But what is, oh, so to go back to that truth table that we had, right, with just these 6 terms when A was greater than B, let's take a look at the case where A1 is equal to B1. So we have 2 cases. Here, A1 is a 0, B1 is a 0. And here A1's a 0, B1's a 0. In every other case, A1 and B1 are different. So here, when A1 is equal to B1 and A0 is greater than B0, then A is greater than B. In this case, when A1 equals B1 and A0 is greater than B0, then A is greater than B. We are doing bitwise comparisons, right? Comparing positionally like bits to positionally like bits, right? We compare the B0s to the A0s, the B1s to the A1s. Similarly, we also said there were 4 cases where A1 is just greater than B1 because A1 is a 1 and B1 is a 0. So in these other 4 cases where A1 is 1, B1 is 0, it doesn't matter what the values of A0 and B0 are, right? That got minimized out of our equation. That's why it doesn't matter. In all 4 of those cases, A is greater than B. So that's why we're able to then say in words, when A1 is greater than B1, we know that A is greater than B. We don't have to evaluate A0 and B0. Right, so schematically, I'm going back to that symbolic representation, right? We had this symbol for our 1-bit magnitude comparator, right? This circuit then takes a single bit input for A, a single bit input for B, generates a single bit output for less than, greater than, or equal to. Right, this is the same symbol down here. All right, so what I've got out here, right, outside this is, remember, A is a 2-bit signal. So this is A 1.0, 1 down to 0. So in the Quartus software, if you want to say that a pin represents multiple bits, you have to use this 1 ... in the schematic. All right, and so coming off of this bus, right, are 2 wires representing A1 and A0. So I just named a single wire here, A0, a single wire here, A1. Similarly, for B1, actually that should be attached there. That's a little typo. This needs to be attached to this, right? But B is a 2-bit signal, right? And I've labeled this one single wire as B0, this one single wire as B1. And so when working with Quartus schematic software, anytime you name a wire, you don't have to draw a connection when you use the same name somewhere else. So here, where I've got A0, down below, when I labeled this wire A0, you can think of these 2 as being connected. It's the same wire. Similarly, this is labeled A1. So anywhere where I use A1, here is this input. This is connected to this. All right. And so what I want you to see is this 1-bit magnitude comparator has 2 inputs, A1 and B1. So this is going to give us the results, right? This output, if we connected to this, would tell us when A1 is less than B1. This output GT tells us when A1 is greater than B1. So I name that wire A1 GT B1. This output tells us when A1 equals B1. So I name that wire A1 EQ B1. Right. Down here, similarly, we're comparing the 0 bits. So A0, B0. This output would tell us when A0 is less than B0. Right. This output tells us when A0 is greater than B0. This output tells us when A0 is equal to B0. Right. I only wired in what I needed for the greater than circuit. Right. And so here's our expression. Right. So we can see coming out of here, here's our A1 greater than B1. This is A1 and with B1 not. Here's that result. That flows into an OR gate, flows into this OR gate here. And then it gets ORed with the expression of A0 and with B0 not. Well, we said this is the same thing as saying A0 greater than B0. So here's A0 greater than B0. And with, well, this is the same thing as A1 equals B1. This is the output that tells us when A1 equals B1. So A1 equals B1 and with A0 greater than B0, that AND gate flowing into this OR gate, flowing into our final output, which I labeled AGTB, which stands for A greater than B. And that's how we could schematically, structurally represent this 2-bit greater than magnitude comparator using 1-bit magnitude comparators. Now, what I would like to ask you to do is to think about, knowing the behavior that we've seen, what would the expression be for a 3-bit greater than comparator? Right, this is to remind you of what the expression is for the 2-bit. And to remind you that we said, well, when or if A1 is greater than B1, or when A1 equals B1 and A0 is greater than B0, then A is greater than B. That's for a 2-bit. We could extend that to 3 bits. And intuitively, then we could extend it to if A2 is greater than B2, right? If A2 is greater than B2, A is going to be greater than B. It won't matter what the rest are. Or if A2 equals B2 and A1 is greater than B1, then we don't care about A0 and B0 because we know that A will be greater than B. Finally, there's another OR condition in there, right? If A2 equals B2 and A1 equals B1 and A0 is greater than B0, then we know that A is greater than B. And these are the 3 different cases that occur in a truth table for a 3-bit greater than comparator, right? Where A is 3 bits and B is 3 bits. And we could then, if we have this expression, this English-like expression, we could turn this into a Boolean expression, right? Here's where A2 greater than B2 or A1 greater than B1 and with A2 equals B2 or A0 greater than B0 and with A2 equals B2 and with A1 equals B1, right? So once you start recognizing some of this behavior, then it's easier to build up other circuits without deriving a truth table. We can then take these relationships and extend them to more complicated expressions is what we're creating, but we have larger inputs, right? Inputs with more bits. Where the truth table gets so big, we wouldn't want to try to K-map it or solve it by hand. All right, so think about that. That can be a lot to wrap your head around, right? This lecture will probably take more than one study, and I'm sure you'll have some homework related to this. All right, let's see how to do this with Verilog. So I drew it schematically for you. Right? Drawing that schematic takes longer, at least for me, than it does to implement it with Verilog. So let's take a look at how we would then create this 2-bit greater than comparator. So what I did is I brought in the 1-bit magnitude comparator that we saw in an earlier slide. Right? So here's our 1-bit magnitude comparator that produces our 3 outputs, less than, greater than, equal. Right? Here is our 2-bit, then I call this GT because it's just going to tell us for greater than, right? It still has 2 inputs A and B that are 2 bits wide. It has 1 output GT. It's going to need some internal signals, right? It's going to need internal signals because if we go back here, see how I named these wires that were coming out of here? So if you want to think of, if we were to draw some sort of black box around this, and so these 2 symbols, this AND gate and this OR gate would be internal to this circuit, right? And we need to then name these connections between the outputs of these modules. So this is a 1-bit module, this is a 1-bit module. Right? We need to then name these outputs so that we can then feed them into the gates that we'll need. So we need some additional logic gates, as we've seen. All right. So let's just look at how we instantiate. So instantiate means then we're going to use another module that we've already created. We say we use an instance of that. And so here, this is just like writing out, this is just like drawing that block symbol for that magnitude comparator. But instead, we use the name of the module, 1-bit mag comp. There's the name of the module, 1-bit mag comp. We give it some sort of unique instance number, right? It doesn't have to start with an INST, but it's kind of easy to remember if we do that. So this is instance 0. And then inside the port list, we have to say what we want to connect. So inside these parentheses, we're using named connection. The dot A, so every signal that's right after the dot or the period, those signal names all refer to the signal names in the 1-bit magnitude comparator. The signal names inside the parentheses refer to the signal names within this module. Right, so we're going to then connect this input A0, right, to an input A. We're going to connect B0 to the input B. Right? If we go back to the schematic, here's where we connected A0 to this input A, B0 to this input B. Right. Now, I didn't draw wires to all of these connections coming out of here because I just wanted you to see the wires that you needed. When you instantiate the Verilog module, right, we are going to have to connect to those other outputs. So that one big magnitude comparator less than, we're going to connect a signal that we named here as a wire type. So this is A0 equals B0, A0 greater than B0, A0 less than B0. So to less than, since we're comparing A0 and B0, I named the signal A0 less than B0. Equal A0 equal B0. Greater than A0 greater than B0, right? So these output signals within our module, right, will be ones whenever, this will be a 1 whenever A0 is less than B0. This signal name, A0 equals B0, will be a 1 whenever A0 is equal to B0. This will be a 1 whenever A0 is greater than B0. Otherwise, they'll be zeros. And so now we need a second instance of our magnitude comparator, right? We had 2 block symbols in that schematic. And so to that A, here's where I want to connect A1 and B1 and get out the results of when A1 is less than B1, when A1 is equal to B1, when A1 is greater than B1. So now that we have these signals generated, we can then write our equation. Here's our AND equation, A1 equals B1 and A0 greater than B0. We OR that with A1 greater than B1, right? And we assign that to this module's output GT. And so that's how we use other Verilog modules, instances of those modules. So we call this module instantiation. Right? And we use an instance of this other module, this other Verilog module that we created. We use 2 instances then to structurally build a 2-bit greater than comparator. Right. And you will likely do something with this in your homework with the less than circuit. And that is actually then the end of this lecture. Like I said, it's going to be left as an exercise to the student. You've been shown the equality comparator, you've been shown the greater than comparator, to go through and implement the less than comparator. All right, thanks for watching.